Hello, this is Mrs. Taylor, and I am going to show you how to determine the continuity of a function graphically. And in order for a function to be continuous, it can have no holes, no jumps, no gaps. It must be unbroken, just like Chowder is telling us now. In your textbook on page 70, you will find this same information, but I just wanted to talk about what exactly continuity means. When we talk about continuity, a function is continuity at a point, a given c value. A function f is continuous at c if the following three conditions are met. So in order for it to be continuous, f of c has to be defined. At that x value, I have to have a defined value. The limit as x approaches c of f of x exists, so it has to approach the same y value from the left and from the right. And then the limit has to equal f of c. So what this means is it has to approach the same y value from the left and the right, and then it also has to approach the same value that the function is defined as at that c value. And when we look at it graphically, it'll make more sense. Also down here is a little note about continuity on an open interval. So when we talk about continuity, we say it's continuous on an open interval a, b, if it is continuous at each point in that interval. And then a function is continuous on the entire real line, negative infinity to infinity, is everywhere continuous. So that would be, for example, like f of x equals x squared. That's everywhere continuous. So down at the bottom we have three examples of discontinuous graphs, and it lists the reasons notation-wise of why these functions are discontinuous. So this first one on the bottom left that we have here is discontinuous. It has this hole in the middle of it, but formally we would say that this is discontinuous because f of c is not defined. So this y value is not defined at x equals c. So I would say that the function is continuous on the open interval a to c and the open interval c to b. For this middle graph, it's got a jump. The function has a jump, so I know it's discontinuous, but formally I would say it's discontinuous because the limit as x approaches c of f of x does not exist. It does not approach the same value from the left and from the right. And then here we would have the bottom right graph is discontinuous, and it's discontinuous because I have this hole here, but formally I would say that it's discontinuous because the limit as x approaches c of f of x does not equal f of c. So it's approaching the same y value from the left and from the right. I have a defined y value at x equals c, but because it's not approaching that y value from the left and right, this is discontinuous. So graphically, that's what that third requirement would look like. A function is discontinuous at a value, so I don't just say f of x is discontinuous. I say f of x is discontinuous at x equals whatever that c value or whatever that x value is. And so there's two types of discontinuities. There's removable and non-removable, and we talked a little bit about this when we went over vertical asymptotes. But let's go back to those same three graphs and discuss whether it's removable or non-removable. Some people like to think of removable graphically. It's like you just pulled a point out of the graph. You just removed one point. So this bottom left, the graph A, this is a removable discontinuity. So that's when f of c is not defined, but every other value is, and it's approaching the same value from the left and from the right. That's removable. The middle graph here is non-removable. It's a jump. It's not just one small point that's been removed from the graph. So that would be when your limit does not exist, when it approaches different y values from the left and from the right, or if we have an asymptote there, that's non-removable. And then this last example, this would be removable because it is approaching the same y value from the left and from the right. We just removed that one y value. And even though it's defined, it's still not a smooth curve. We have to pick up our pencil in order to follow every defined point. So all of these would be discontinuous, but only the middle graph would be non-removable. The left and right would be removable. If I can define the function in some way to fill the hole, it is removable. So if this was my function on the bottom left and I wanted to make it continuous, I would have to use a piecewise setup in order to fill that hole. So let's look at a few examples. These problems are from page 78 in your book, and even though the directions want you to determine the limit, let's discuss the continuity for purposes of this video. So for number 1 and number 2, there are no holes, there are no gaps, there's no jumps. Therefore, for number 1 and 2, the function would be continuous everywhere. So I'm just going to write here, continuous everywhere. 3 and 4, they are both discontinuous, and it's a removable discontinuity. We have just that singular point missing or removed, and for both of these it's defined. We have a y value, but it's not a situation in which the limit is equal to the y value. So I would say, for example, number 3, I would say f of x, well, instead of saying is, let's say has. So f of x has a removable discontinuity, and I need to define where it's located. So removable discontinuity at x equals 3. And to be really thorough, we could provide the reason. So I would say because the limit as x approaches 3 of f of x does not equal f of 3. So the limit does not approach the same y value as the function is defined at x equals 3. So that's how I would establish the continuity of the function. Sometimes when you're talking about continuity, you're talking about where it's discontinuous. I could also say, for number 3, the function, I could also say the function is continuous on the intervals, and we are to assume that it's continuous through infinity to the left and to the right. So I'll say from negative infinity to that x value, which is 3, and from 3 to infinity. And I leave these as open intervals because it doesn't include x equals 3, because that's where it's discontinuous. So those are the two ways that you discuss continuity. You discuss the intervals that it's continuous on, and the x values at which it is discontinuous, and the types of discontinuity. So that would be the way you would look at continuity graphically.